So, I'm going to present a case study on the issues related to foundation of a big structure like aqueduct. This aqueduct that you see in this photograph is basically an aqueduct on the Orson River that is in the phase 1 of the Sardar Sarovar project. It's a very huge aqueduct as it is seen in the photograph. And this large structure, how much damaged it was, and that in the foundation and how it could stand, that I am going to present before you. What kind of issues be there in the foundation of a large structure, and how evasive the things are, that I can explain to you through this paper. The length of this aqueduct is about 481 meter, that is the gauge width of the river, and 27 spans are provided in this structure. So basically it's a bridge carrying water, so to speak. Total there are 26 piers. Each pier is provided with 44 piles. The depth of the pile is approximately 15 meter, albeit somewhat varying as per the real rock at the bottom, and all are the varying piles. How the erosion took place. Basically, the sand of the Orson River is of very high quality, and that's why in order to prepare the standard sand, people are enticed to carry it. So it is sand mining, and that too very heavy, legally and illegally as well. And it's not a case of erosion, truly speaking. It's basically a case of sand mining, and that's why so deep has gone the river bed. I can show you a bridge called Sankheda Bhadarpur Bridge of road just 17 km down the line in the structure. This is the bridge, and you can see here how deep the river bed has gone. It is approximately 7.2 meter. 7.2 meter. Just river bed has gone down, and this much of sand mining has been done. Now this structure, aqueduct structure itself, 17 meter upstream of this bridge, it is having around 2.8 meter of so-called erosion. It is not erosion, it is sand mine. And this is the real depth of the sand that has been carried away. You can see the state of the piles. This is still a good condition of pile as compared to other piles. I can show you further how much damage has occurred and how the damage has occurred. Basically the river bed took a bowl kind of shape. Obviously in the bowl the velocity is increased. Because of the increased velocity, the hard sand particle strike like bullet with the concrete surface. And that's why there was initially the beating, followed by cavitation and erosion and all other faults. But this was the state of the pile in 2013 when we inspected it. The reinforcements were also eroded and they were thinned down. Diameter was reduced drastically. So this was basically a problem. Then how the consequences were made assessment of. What would happen? What would be the obvious consequences of this kind of situation if permitted to continue for a long? That was tried to be understood by us. And finally at the end of analysis, we worked out that, the pile, because they were load bearing, obviously they were. In case some 2, 3, 4 piles cease to take load, or they fail, obviously there would be moment and force redistribution as per our basic principles of structural engineering. These are redundant structure. So there will be a redistribution of forces and moments, and if it takes place, then not the pile that is likely to sink, but the adjoining piles likely to the pile that is going to sink will be affected, though they are apparently looking safe. And this is perhaps the limitation of any redundant structure, that the safe looking member will undergo failure. Not apparently failing looking member would undergo the failure, but apparently looking safe member will undergo failure. So that is basically a limitation of any redundant structure, but the biggest benefit that you get out of the redundant structure is that because redundancy is too high, so many members are there to share the stress, and that's why the distress and stress both are distributed. So this structure, so to speak, is standing in spite of having so bad piles because the redundancy level is too high, integrity of the structure is too high. I'm just